Okay, so now let's get some engineering quantities out of this expression. Okay, so first, what's the maximum velocity of the pipe? What's the actual value, right? We already know it's a quadratic profile because this term's squared, so it has, right? Now we actually know what the curvature, what this total function looks like, and it has this right here, right? So the question is, how fast is this center line? Right? Already agrees before because we said right here when the radius measured from here was equal to 0, we had no shear, right? We had the lowest amount of shear, so there's the lowest amount of added forces resisting the flow, so it should be the maximum. Here it's pretty easy to see when it's a maximum because this right here, this is always greater than 0, right? It's greater to or equal to 0 because it's a square quantity. So right off the bat, quickly, you can just show that, right? Usually you can just show that the maximum is when this term right here is 0, right? So, right, how fast, right? What's the fastest point in the fluid? It's just simply this term right here. Boom, right? And that's a pretty easy thing to do because this is measurable right here. You can just take 2 points and measure pressures at the end of pipes. This is a distance. Diameter is easy to measure. This is easy to measure. So if you just have fluid running through a pipe, you can actually tell someone what the fastest fluid through there is. Velocity is cool and all, but really what we care about is flow rate, right? So flow rate, or volumetric flow rate is the easiest one, right? Before, maybe in classes, you just said that this was, right, the area times the velocity. And this is true. This just this multiplication of two numbers is true if your velocity profile, right, is straight, right? If this is what your velocity profile looks like, where this is a straight line, right? That's when this is true. But since ours, right, this is what ours actually looks like, where it's changes. You have to do integration to figure out this term. Not that bad though, just that's the idea. Okay, so volumetric flow rate, the way you express this now instead of that, right? Integral dA, where this is the surface integral. So this is from 0 to r. Remember for integrating in calculus, for integrating this little shell of cylinders, you get this expression, right? And then if you do this integration, so that's extra credit, right? Actually, the steps. We'll just say that now because we live in a world of, right, Mathematica and a bunch of sources that can do this stuff for you. So you can do it that way, or you could actually do it by hand. Okay. So now I can tell you what the flow rate is based on pressure gradient. And the only thing that you should really recognize here is that this is a fourth power relationship. So that's very sensitive. And that's a fundamental thing about pipe flows, is changing the diameter has huge consequences when it comes to the volumetric flow rate, right? For the maximum flow, it was squared in this pressure gradient, but the pressure gradient doesn't affect the flow rate at all. It's the diameter, and that makes sense because it's volumetric flow rate. So since it's incompressible flow rate, if you ever want to get the mass flow rate, m dot, right, what do you gotta do? You gotta take density times the Q. But for incompressible fluids, usually you just work with volumetric flow rate because you're just one number away, one multiplication away. So that's the big takeaway from the flow rate here, is this d is raised to a fourth power. These are just coefficients. This didn't change. This didn't change. Still, flow rate is linearly proportional to dp dx, right, to the fourth power for Q, with all the assumptions we made about this analysis. So up next is what you want, because I don't want to do it. I don't want to do the integrals. I liked in my sophomore year, I liked it when plyometric flow rate was cross-sectional area times the velocity. I'd rather just do this. So what we do is you then figure out, okay, well, what does this velocity have to be? What, right? Essentially, we're saying, give me, right? In real life, the velocity profile looks like that. So, but I want to just figure out what constant velocity profile gives me the same flow rate, right? So I want to figure out, that's a U of R right there. But what we're going to do, what the next calculation we're going to do right now is we're going to say, tell me right? We're going to say, just imagine that it is just a totally constant velocity profile, right? Where this now, U of R, sort of mean U of R is equal to just the constant value of this V bar. We're going to say, calculate this now based on the analysis we have. Okay? So the way you do that, right? You just write out what you want. I want one of these. A, so solve for this. Okay, not too shabby because this is just this. 1 over A. Okay, and this was an integral, right? And we'll rewrite that. So we have that. So this is divided by the area right here. Do the steps, do the integration, right? The area is pretty easy. It's just pi, right? This is right area, because we're talking about a cylinder every time, so that's not too bad to calculate. What do you get? You get that it's half the maximum velocity rate. But it doesn't matter that it's half, just matters that you can write and figure out what this V bar is. And that's what we're going to use a lot throughout the rest, because we need the fact right? Theoretically, we need it to be the case that we're just considering a constant velocity profile, not a curved one.